Welcome back. In this video, I wanted to make like a brief introduction into how you can make some simulations in Tina, in particular for the operational amplifier and for the filter that you need to make for your homework. So I will first start with the operational amplifier. In general, you will need three main components. Remember that in Tina, you can search for the components in this bar at the top of the Tina window. And well, you will need for the basic components, you will need the resistor. You can click on the resistor and drag the element into the workspace. Also, you will need sources. In particular, you will need the voltage generator. That is the symbol. Okay, this is the symbol for the voltage generator. And well, you will need this voltage generator in order to generate the sinusoidal or the input voltage that we want to amplify in order to make the simulation. Uh, Furthermore, you will need the operational amplifier. No, remember that the operational amplifier is the device that can help us to amplify the input voltage. And for the homework, you can use the non-inverting amplifier or the inverting amplifier as you prefer. In this simulation, I already make the circuit for the non-inverting amplifier. And well, you can search for the operational amplifier in the semiconductors option in Tina at the top of the window, and then you need to select the ideal operational amplifier, that is this symbol, and you can drag the element into the workspace. After that, you can connect the components that we have here in the for the operational amplifier, and here is the ground. You also need the ground that is also here in basic and is the first element that you can see here. No? And also you can drag the element into the workspace. And remember that for making the connections, it's relatively simple. You only need to place your cursor in the top of in one of the terminals of one of the components, and then you can click on that and then move the cable to the other terminal of other component. And well, here I make the simulation for the non-inverting amplifier. You can see that this is the same diagram that I placed for the presentations during class. And well, after that, if you want to see if the operational amplifier is working as expected, you need to go here to analysis, and then you need to click here on transient. And well, here in this window will appear, and you need to place the starting time and the end time. Here I select a value of 2 for the starting time, and the end time will be 2. And then you click OK. And you will notice that the following window appears, in which we have the two waveforms, the input waveform and the output waveform of the operational amplifier. And also you can place legends in order to identify these colors more easily. In this case, the input voltage is the green waveform, and the red or brown waveform is the output voltage that, well, in this case, is labeled as BF1. Okay, that is the output voltage that we are measuring in this part. Also, you can see here that I am using a voltage meter. So if you want to place this voltage meter or this voltage pin, you need to go here to meters, and the first part is the voltage pin. You can drag this element and connect this voltage pin in whatever node you want to measure the voltage of the circuit. And that's it. Okay, this is for the input and the output waveforms. For the operational amplifier, you can see that it's relatively simple to perform the simulation. And I think that's it. Okay. Remember that in order to make the design of the operational amplifier, you need to follow the formulas for the non-inverting and inverting amplifier in order to set the gain that you need according to the data of the problem. And now I will show you how you can simulate the filter. The components for the filter are lower. No, and also are more common. There are the resistance, the capacitors, and also you need the input voltage generator. Um, well, remember, I will go back to the operational amplifier. You need to set some parameters for the input voltage. So you can click here in the input signal, and in the signal, you can define the type of waveform that you want as the input waveform. Well, we have here the sinusoidal, the square, the triangle, and other functions that you can select, not like this step function or this input function. Uh, for practical purposes, for simplicity, I am only using a cosine function. You can use also that. And remember that you need to select the amplitude of your cosine function, the frequency, and the phase. Okay? And well, a similar process needs to be done for the input waveform of the filter. Again, if you double click on the voltage generator, remember that this is a voltage generator. Here I am using a cosine function. And again, you need to define the amplitude, the frequency, and the phase angle. And in this case, for the simulation, well, you need to define mainly the frequency of the sinusoidal and the amplitude. And after that, you will need to use, you need to set the resistor and the capacitor. Remember that for searching for the resistor is here in basic. You need to click on the resistor, and also you need to place the capacitor that has the following symbol. So you can drag these two elements here. You double click on the resistor and you can change the value of the resistance. And also you can double click on the capacitor and you can change the value of the capacitance. So I will erase all of this for now because I already connected these elements. Also, notice that I am using the configuration of a low-pass filter. This information and the way it is connected is available in the presentations that I uploaded to Canvas. And what else? Also, well, this is the same circuit that I showed you in the presentations. That implies that the cut frequency of this circuit is 2 Hertz. And also, this is a low-pass filter. So that means that, when I introduce an input waveform, no, when the frequency of the input waveform is greater, and let me erase all of this. Okay, when the frequency of the input waveform is greater than 2 Hertz, the amplitude of the output waveform will be reduced. Okay, but when the input frequency, no, the frequency of the input voltage is lower than 2 Hertz, the amplitude will be the same. That is, the output amplitude will be equal to the input amplitude. Okay? Because we are not performing a reduction or an attenuation of the output voltage with respect to the input. But since this is a low-pass filter, when I introduce an input voltage that has a frequency greater than 2 Hertz, you will see, if you analyze the plots of the waveforms, a reduction in the amplitude. So, well, we can simulate all of these effects using this circuit as a basis. And also notice that, well, you need to place your input voltage, that is the voltage generator. And to measure the output voltage, you need to measure the output voltage at the terminals of the capacitor. That's why I am using this voltage pin in order to measure the voltage of the capacitor. And what else? Well, we can make the transient analysis again. And well, we can click OK. And here you can see that, well, here I am defining a frequency for my input waveform that is lower than the cutoff frequency. And since this is a low-pass filter, I can see that I have a similar amplitude between the input and the output. We can also place legends on this waveform in order to analyze if the behavior is as expected. And you can see that, well, in general, the input voltage follows very closely the output voltage because we are not attenuating the output voltage based on with respect to the input. And also, well, here I am defining the frequency. No, you can see that, well, the frequency is 100 millihertz. That is lower, no, than 2 hertz. That's why the amplitude is not of the output voltage is not attenuated. What if I change this frequency, for example, to 30 hertz, and I click OK, and then I plot the transient behavior, um, and I click OK. I am only changing the end time because the sinusoidal will be oscillating much faster. And so I will click OK. And you can see that now the output voltage has a lower amplitude compared to the input voltage. And that is a consequence of the filter, no? Because I am introducing an input sinusoidal that has a frequency greater than 2 hertz. And for this part of the simulation, I use a value of 30 hertz. And finally, um, if you want to generate the Bode plot or the frequency response of the filter, what you can do is to go to Analysis, AC Analysis, and then go to AC Transfer Characteristics. And well, you can set the parameters as follows. I am defining the start frequency as 10 millihertz and the end frequency to 1 kilohertz. And well, then you need to select the sweep time as logarithmic, and the diagram, we want to plot the amplitude and phase Bode plots. And well, you will generate this graph. And here you can see the behavior of the low-pass filters. You can see that in this region where we have 0 decibels, we are not performing any attenuation in the output waveform. But as you increase in frequency, there is an attenuation because we are reaching the negative decibels. No? That means that the output voltage is lower compared to the input voltage. And also you can use this cursor and place this cursor around the region of the 2 hertz of the 4 hertz. Let me move this. So this is the, sorry, I mentioned previously 4 hertz, but remember that the cutoff frequency is 2 hertz. So in this, beginning from this point, we can see a greater decay in the output voltage compared to the input voltage because we're increasing the negative decibels of the filter. Remember that the negative decibels are associated with a lower amplitude in the output voltage compared to the input voltage. And this is the region that you need to analyze. Well, you can place the cursor in order to analyze where the cutoff frequency is placed along the Bode plot of the filter. And also you can use this Bode plot in order to verify that your circuit design is correct. And what I think that's it. I hope that this video is helpful for you to making the simulations in Tina. Also, I only wanted to point out that, well, one of the points of the homework is that you need to combine the two circuits. So I only make like an overview how this process is done. What you can do is to copy the filter. You need to click Ctrl and C and then Ctrl V, and you can copy the filter. But we want to combine the amplification with the filtering. So to do that, we can connect the output voltage of the amplifier and connect it to the input voltage in this way. And in this way, you can combine both the operational amplifier effect with the filtering effect, okay? Basically, we are transferring the input voltage is placed in the operational amplifier. This is the output voltage of the operational amplifier. But for the filter will be the input voltage that we are connected into this part of the circuit. And then, well, the output voltage that we want to analyze is the output voltage of the filter. That for this case, since this is a low pass filter, we want to measure the output voltage in the capacitor. And that's it, no? And well, I hope that this video is useful for you to make the homework. If you have some questions or doubts related to this, or you have a problem with the simulation, you can ask me. So see you later, and I hope this video can be helpful for you.